Good day, everyone. Today's presentation is on ETAP GIS and mainly on how to utilize ETAP GIS to better design, analyze, and expand transmission and distribution networks. Before we jump into talking about GIS, I'd like to specify a little bit of the fundamentals. In power engineering, a single line diagram is an electrical drawing representing the electrical devices or assets of a power distribution system. The electrical diagram is represented by symbols and describes how these electrical devices are connected and related. Sometimes a single line diagram of an electrical installation is also called a one-line diagram or OLD. A single line diagram provides a fundamental representation of a blueprint of a three-phase power system. As the term suggests, a one-line diagram uses a single or one line to represent all three phases. Now, a digital twin is essential. It's essentially utilized for preparing a critical response plan with validated model. Enables personnel to understand and design the electrical distribution system, and it's also a roadmap for future testing, service, and maintenance activities. So digitizing a single line diagram is the foundation of the electrical digital twin for design and operation. And this presentation will focus on how to digitize that single line diagram by importing it from an existing GIS database. Now, the reason why this is so important is because typically for small commercial or industrial applications, it's pretty easy to create a single line diagram by hand, or maybe import it from Aviva Electrical or from AutoCAD Electrical. But when we're talking about transmission and distribution networks, we're talking about thousands, if not millions, of electrical nodes, buses, components. So it would take a power engineer many months, if not years, to generate or develop a single line diagram. So what ETAP GIS performs is the ability to extract the electrical layer of data from a GIS database like ESRI, ArcGIS, and provide connectivity, impedance information, and develop and generate a single line diagram. Essentially, what is ETAP GIS? It is connecting the GIS world to the ETAP analysis tool. It's that bridge of importing the data, generating the model, so that you could perform ETAP analysis modules like power flow, short circuit study, feeder hosting, and so on. Now, combining a generation, transmission, and distribution system. So you could actually display in ETAP with ETAP GIS, not just transmission, distribution, but also generation, right, inside the fence. Now, ETAP GIS is combining the GIS view with logical view or OLV. So as you could see here, we have the logical single line diagram combined also with the GIS. So to a little bit better understand, let me explain what a GIS or geospatial view is. It's a view of the electrical grid imported from an existing ArcGIS or ESRI database, saving hundreds of hours on recreating the model from scratch. And that's what we're looking at on the screen here in the center. Now, on the left is what most of us are used to seeing, a typical radial view representation of the single line diagram or logical network view. And then over on the right-hand side is the net view or the network view, which provides the engineer and operator with a very clean, organized view of a very large transmission and distribution network. And these are the three visualization views that ETAP actually provides for the user. Now, the case for why GIS to ETAP. Number one, reduce data entry cost by using GIS updated engineering data for system studies. Importing your existing GIS data into ETAP to create an intelligent geospatial electrical model for design and analysis. And more importantly, the generated electrical model is ready to take advantage of ETAP situational intelligence. And we'll talk about some ADMS applications towards the end of the presentation. Again, continuing why GIS to ETAP. ETAP performs an automatic error correction for voltage and phase, which avoids duplicate and incorrect data entry. So it basically cleans up the data. It supports 3-phase, 2-phase, and also single-phase. It'll validate the GIS electrical system per required parameters and study the system for utility customer requirements as well. GIS Data Sources, the main data sources for ETAP GIS is going to be ESRI ArcGIS, CIM, which is a common data model language for information exchange in electrical utility industry. It also supports IEC 61970 and IEC 61968 standard. Multispeak, which is a specification or standard that defines a standardized interface between software applications used by rural electrical utilities or co-ops, and also Excel as well as KML data formats. How the intelligent data mapping works is you have the various sources on the left-hand side. There's a universal mapping tool that is the bridge to take the data from the source, whether it's CIM, Multispeak, or Excel, ESRI GIS. It'll go through a universal mapping utility, and then ETAP will generate both the electricals, the geospatial view, as well as the substation view and the network view that I showed earlier. More importantly, incremental data updates, which are essentially you are able to schedule updates to stay up to date with the GIS database. The workflow is the GIS database is the universal repository of all the information, not just electrical, but also water, gas, and many other disciplines. And essentially, as the GIS team updates the electrical information and all the information, then ETAP automatically connects to the GIS database and performs incremental data updates. So in this way, your ETAP model always remains up to date with the GIS database. Now we can talk about some of the design and analysis tools that are supported with GIS. And number one is going to be the unbalanced power flow. Unbalanced power flow is typically required due to many single-phase laterals. It supports upwards of 10 million components. The study can be completed on a partial system. It supports equipment sizing. Alerts are supported, also multiple visualization techniques. So I'm going to actually bring up ETAP GIS and just quickly show on the left-hand side, I have the logical view, right? This is what a lot of our power engineer users are very comfortable, or this is what they're used to seeing. So you see the radial representation with all the loads here on coming off of different buses through cables, through transformers, and then you have your sources kind of all the way on top. So it's a typical radiological system. Now over on the right hand side is the source for this. You'll notice that we could have Google Maps, for example, in the background, and we could see geographically where the line is located. We could see where the substation is located, where the different loads are located, right? The logical representation is automatically generated from the GIS and all of the connectivity as well. Now, we could actually run the most basic, or actually the mother of all studies, which is the unbalanced load flow. Unbalanced load flow will not only provide you with the voltage drop, power flow information, but it will also provide us with alerts. So anytime, for example, a cable or a protected device frame is overloaded, you'll notice that it automatically flags those components as red on the logical view on the left. And then it'll provide you with an alert view here on the bottom so that you could quickly spot and fix any deficiencies on the system. This is very common the first time that you import the data from GIS. A lot of times, maybe instead of a 100 amp fuse, the person doing the data collection put 10 amps, right? They missed a 0. So errors like that will automatically be caught by the unbalanced load flow engine. Over on the right hand side, we can also see, we can also visualize the different loads, transformers, protected devices, and you could also see how the power flow, right, graphically is going from the source to the different loads. All right. So just wanted to show everyone the different views between the ETAP logical single line diagram and then the GIS and how they're both tied together. So continuing on with the types of studies that are available is unbalanced short circuit. This study type accurately models unbalanced networks, especially transposed lines and unbalanced shunt devices and sources. Also, it'll do a simulation, series compensate lines, simulate simultaneous faults. So if you have multiple circuits on the same pole, you can simulate simultaneous faults on that, and also you can perform study faults at several locations. Next type of analysis that can be done is load allocation. The ETAP load allocation software considers automatic meter readings, AMR 15-minute of kW and kVAR demand, combined with a number of methods to allocate the load correctly for each load point. Actually, most power flow programs that are used to study power systems from the substation down to the primary terminals of the distribution transformers. And they tried to figure out what should the load be for each transformer. Until recent years, the only information that engineers would have about the load would be the transformer kVA rating. In some cases, the kW per hour consumption of each customer was known in addition to information on which customers were connected to each transformer. With load allocation module, ETAP can use the existing meter and also the model information to estimate the load at each customer. Also, time series unbalanced power flow. It is the time domain unbalanced power flow or time series distribution load flow simulation that is used for the purpose of varying load and generation in the system and solving the steady state power flow in the system over a function of time. Time series unified power flow analysis module includes key features such as single year load growth analysis, multiple year load growth analysis, and also solar and wind farm annual yield and losses estimation. We're going to quickly go over a demonstration of this. Here we have the time domain load flow study and then the study case. We go over to the event tab, and here we can actually specify actions such as a circuit breaker or a switch opening and closing. If we go over to the time domain loading tab, we could specify, for example, external data as the source for generation and also loading. And also here we can specify plots for individual devices. So right now we're looking at lump loads. We can, for example, check all or display as part of the plot all the lump loads, but in this case we're only going to select 3 lump loads. Now if we go over to the sector library, we can assign different profiles, single year, multi-year, interruption, outage cost. We can also go with different profile libraries. So for example, commercial, industrial, residential, and you could see over on the typical values on the right hand side. Now if we go into each individual load, we can specify the time domain based on sector or based on external data. If we go based on a sector, we can then specify the multi-year forecasting. So the date for energizing and out of service. And then if we go over to the time domain for lump loads and select, for example, a typical, we can see how the over time the load changes, right? So it's basically running a power flow as a function of time. Now, as part of the time domain power flow, you also get the alert view, and you can also get to do the plot manager, which you get to specify, for example, the voltage for a given line or feeding a particular load, and see that as a function of time, right? Whether you make it into a residential, like a residential load, or an industrial commercial, or if you specify your own source and also loading parameters. All right, now moving on with another analysis module within ETAP that takes advantage of GIS is reliability assessment. It performs the calculation of system and load side reliability indices, calculation of sustained and momentary load and source reliability indices, considers multiple failure and repair rates and outage cost. It supports single and double contingency, and its sensitivity for ranking and plotting. So here is a brief demonstration how to perform a reliability assessment using ETAP. We're going to mainly work on the logical view. We double click on the transformer. We go over to the transformer's reliability tab, and we could specify the mean repair rate, the momentary failure rate, the mean to time failure, the mean to time repair hours. A lot of times this information is not known, so you could just simply go into the typical library from the goal book. Again, if we double click on each load, this information can be gathered from the goal book library that is preloaded in the program. Or you could specify that your own if you have an asset management program, for example. The method you could specify is single contingency or double contingency level, max momentary duration, failure rate duration, and then here you get to specify how to plot the results. Once we've run the reliability assessment, we can clearly see on the logical view over on the left-hand side, the failure rate per year or per hour, depending on how you have the option set up, right? Right now we have an average failure rate. We can also select expected energy net, and then you could see how the results automatically are updated on the single line diagram. And we can also look, for example, at momentary index like MAFI or MADI, failure per year or per hour. Additionally, once that information, those indices are displayed, we can also create a very comprehensive crystal report, which is formatted in such a way that it provides the indices up front, and also it provides us with the ability to do a plot. Here we're about to do a plot selection of the entire system. We specify the plot time, and here we can see the sensitive analysis for expected energy, or EENS, being displayed for the results. Okay, now moving on with the next analysis type is protection and coordination. The ability of being able to do a sequence of operation for arcing fault and as well as bolted fault. You could see over from the animated one-line display that you could specify a location where to place a fault, whether it is a single line to ground or whether it's a line to line or a three-phase bolted fault. You could place the sequence of operation indicator or that little lightning bolt, and ETAP would provide graphically the sequence of events. Here we see a fault, the first device to trip, then it will show the second device to trip, and in the rare event that those two devices were to fail, right, you could see the sequence of events. Also, Following the protection and coordination is the ability to do arc flash, right? Especially on some of these locations that are well above the 15 kV, which falls outside the IEEE 1584. The ETAP's high voltage arc flash module is called ArcFault, and it provides the ability to do line to ground arc faults on locations that would be outside of the IEEE 1584 standard. So typically locations that are above 15 kV. It also provides the ability to do a three-phase open air and enclosed equipment, again, of course, above 15 kV, and it's compliant with OSHA 1910.264 Appendix E. Simulation, you could perform a simulation of arc current, voltage, and protected device operation for line to ground, line to line, and line to line arc faults. Working distance and clearances with transient over voltage. Here is a quick demonstration of the sequence of operation for the high voltage arc flash module. You see that you as the user can perform a sequence of operation, a quick simulation, and ETAP would provide not just with the graphical view, but also it'll provide you with a comprehensive text report. This system here definitely falls outside of the IEEE 1584 standard. All of these locations are well above 15 kV, and with this particular module, you would be able to perform high voltage arc flash on those locations. Okay, now moving on to the next analysis module is volt-var optimization, or VVO. Volt-var optimization and control finds and sets the optimum settings of voltage and VAR control devices, LTCs, voltage regulators, switch capacitors, in distribution system. Considering objectives and constraints, it is a centralized volt-var optimization for distribution management system, DMS. Main objective of volt-var optimization control is to make distribution grid more efficient by decreasing power loss and to reduce utility costs by reproducing peak demand or conservation of volt reduction, CVR. The concept of VVO and CVR is to maintain these voltages and the phase lag within certain limits or specified values by using tap changers or by reactive power injection. These voltage limits or specific voltage at various locations in the distribution system are calculated using optimization of the mathematical models of the system. A concept of VVO and CVR, the principle of CVR is that saving in energy consumption is achieved by a reduction of voltage level without affecting the performance of the customer's device's demand and minimize the system losses. This means that total power demand can be reduced by operating in the lower allowable range of the voltage as shown in figure number 2. The objectives of this particular analysis module, VVO, are to maintain voltage within limits, minimize voltage drops, optimize power flow, real and reactive, reduce losses, improve power factor, optimize transformer fixed taps, low tap changers, and generator set points, and minimize component or circuit overload. VVOC finds and sets the optimum setting of voltage and VAR control devices, optimizing volt-var and distribution network by adjusting the low tap change per voltage regulator and capacitor, bringing up voltage levels of system by changing tap positions on transformer, reducing the VAR flow to minimize overall voltage drop, and reduce power loss, minimize overall voltage drop. Volt-var optimization includes conservation voltage reduction, or CVR, functions that is used to calculate and maintain acceptable voltage, for example, 120 volts plus or minus 5%, at the service entrance of all customers served by the feeder under all possible operating conditions. CVR is used to flatten voltage profiles and lower overall system voltage while staying within the specified ANSI or IEC voltage limits. Overall system demand can be reduced by a factor of 0.7 to 1% for every 1% reduction in voltage. From a consumer's perspective, this reduces the energy they consume. From a utility perspective, it reduces the amount of power they need to generate or purchase from a generator. Minimize power loss, stay within voltage range while minimizing losses, but fluctuate when load predictability is unknown. Just keep voltage close to normal within voltage swings. The CVR factor of 1 means for 1% of voltage drop, 1% of voltage drop in energy results. A positive CVRF is desired. And then we could talk about the next analysis module that takes advantage of a single line diagram being generated from a GIS system. Is feeder hosting capacity. It provides guidance when a detailed study is necessary. Each feeder would have a unique hosting capacity. Feeder characteristics determine issues that occur. It's impacted by voltage or line regulators, impedance, the location of PV, and no correlation between hosting capacity and peak load. Continuing with feeder hosting capacity and feeder DER accommodation. How much power DER a feeder can accommodate without violating the criteria. The purpose of feeder hosting capacity analysis is for studying the impact of distributed energy resources, or DER, to the distribution systems. The impact is unique to individual distribution feeders and is based on certain issues ranging from voltage, loading, power quality, protection, and control. ETAP will provide integrated solutions for DER evaluation and approval. This is a typical small-scale distribution system with a solar panel installed to every household. ETAP is capable of providing the calculated hosting capacity at any circuit level. The capacity can be calculated for the entire system, for a certain branch, or even for a bus node. All solar panels will be used during the study. If no solar panel was found in the area, then the capacity would be 0. And finally, we arrived to the conclusion, which is why take GIS data into ETAP, right? And number one is to reduce the data entry cost by using GIS updated engineering data for system studies. Import your existing GIS data into ETAP to create an intelligent geospatial electrical model for design and analysis. And more importantly, the generated electrical model is ready to take advantage of ETAP situational intelligence. And what I mean by that is advanced distribution management system, as you could see here. So under network optimization, we could see, for example, what we saw earlier, the VOLVAR control, load management, DER integration. Over on the right-hand side, we saw the distribution network analysis. So, for example, protection and coordination, the unbalanced load flow. And then down below, we have management planning. So long-term load forecast, optimum capacitor placement, optimum power flow, technical and non-technical losses, reliability assessment. And over on the right-hand side, finally, is the operator training, right, or EOTS. And that is, once you have an ETAP model, you could do software in the loop, and then you could train dispatchers. You could use the model for root cause analysis, for event playback. You could use it as business interface, AMI integration, and also backwards integration with GIS. And all of this is put together at the core is the network operation and control functions, right? So the ability of visualizing all of this information, not just in GIS, but also as a logical view. And finally, Just to wrap things up, the GIS Data Import Service. Please contact us directly for more information on these services. We know that a lot of times this is not something that you may be doing on a daily basis, but if you have the need of importing data for analysis purpose in ETAP, we actually have the in-house expertise to perform that for you. So please keep that in mind. And with that, thank you everyone for attending this presentation.